right, so in this example of a worked out combined concept, I'm going to work through this problem as I've shown. So I start out with a mass M that's initially at the top of this hill over here, and then the mass is going to slide down the hill and then collide with a second mass that's initially at rest at the bottom. So then they collide, and then the two masses together, this is all frictionless, slide up and over this second hill. And the question is, what is the maximum height of the first hill such that the blocks don't lose contact with the road at the top of the second hill? Okay, so we have a couple things going on here. So there's a couple things that should catch your eye immediately in terms of problem recognition. One of them is a vertical circle. We have a vertical circle, so that means that we are going to be using Newton's second law and conservation of energy kind of combined together. So we know that in this portion of the problem with the vertical circle, we're going to have Newton's second law and conservation of energy somehow at play. We also should have this idea of like, oh, a change in height from the initial mass to the second mass. That also should ring some conservation of energy bells. And then from this module, the idea that there's a collision. A collision should right away trigger the idea that you're going to be using conservation of momentum. Okay, so let's go ahead, and because I chose this problem for a couple reasons, I wanted to choose one where the end goal is actually on the initial side of the motion. So you can see kind of what might happen if we start to work backwards through the motion to solve for something initially. It's still the same process. You're still breaking this into parts. And then the other reason is because it's a very typical combination of energy and momentum, but then also with a little bit of Newton's second law thrown in because of our circles. So because I'm going to work backwards, because I'm going to try to work towards what I want to find and start with what I know, I'm going to label my point over on the right as, say, point A. And then I'm going to label here, in terms of dividing this into our concepts, I'm going to have a point after the collision, right? So this is going to be after my collision at B. And then I have to have a point before the collision. So I'm going to call that C. So that's before the collision. And then I'm going to start over here at point D. And you can do this however you like. And you'll see with my subscripts that sometimes they just become words, like whole words describing where something is. But if you want to label it as A, B, C, D, then you can have velocities at each point, etc. Now we want to think about a plan. Well, my end goal here is to get H max. And if we kind of look at this, like I had said here, is that this first portion coming down, this is going to be a conservation of energy step, you know, from the point on the top of the hill to right before the collision, right? And then I'm going to have a conservation of linear momentum step, which is going to be for the time during the collision. So that's going to be used during the collision. And then it's going to go up and over this hill. And so after my conservation of linear momentum, I have another motion up a hill. This is going to be conservation of energy. And then at that specific point, I'm going to use Newton's second law. So hopefully, as you've been practicing this skill, you're developing, you know, ways to recognize when to use which concept. A couple things to keep your eyes out for. Changing in height. You notice the two changes in heights are my conservation of energy steps. My collision, when I have a collision in here, then that's always going to be my conservation of momentum. In this case, linear momentum, because nothing's rotating yet. And then also, when I'm told information about a force at a particular point, in this case that I don't want them to lose contact with the ground, then that's a single point that I'm going to be using Newton's second law to analyze the motion. So you start to get used to these things that show up that let you know which process to use when, and then we can combine that into our well thought out plan. So because what I want is on the initial side, and you can work initial back and everything will be terms of that unknown. It's totally fine, but I'm going to show you a way where I'm going to work backwards. I'm going to first use Newton's second law with the normal force going to 0, right? Because that was the whole point, that it's not going to lose contact at the top of the hill. So Newton's second law with normal force going to 0 and circular motion, and I'm going to get the speed at the top of the second hill. Now, I find this to be very useful to note when I have a collision, whether or not it's both objects or one object, because then I'm going to remember it later. In this case, the mass is going to be 2m. Both objects stuck together. That way I can keep track of it. So that's just a little thing I do. All right. Then after I know the speed at the top of the hill, then I'm going to use energy to get the speed right before the collision. So I can kind of work backwards in time, and that's okay because initial equals final, so final equals initial. It doesn't really matter which way I go with my energy or my momentum, my conservation laws, right? So I can then say I'm going to use conservation of energy to get the speed of both blocks just after the collision. So that's going to be that point marked after. Then I have the collision to deal with. So I'm going to use conservation of linear momentum, and that's going to let me relate the speed after the collision to the speed before, to get the speed before the collision. And that's going to be the speed of a single block of just mass m right before that collision. And then the last step is I'm going to then have the hill part. I'm going to use my last change in height, my last energy, conservation of energy, to get H max for my normal force going to 0. The height I will solve for then will be my maximum height because I set my normal force equal to 0. All right, so let's go ahead and execute all of these steps. So I'll start with step 1, Newton's second law at the top. Well, my normal force would be up. My weight is down, and it's equal to 2 mg because there's 2 blocks stuck together. You could even draw 2 blocks to remind yourself if you want to. And my center of my circle is downward, and so my acceleration is v squared over r. I'm going to take my positive r direction to be downward, as I often do with circular motion, and my normal force goes to 0. So that's going to give me n, and then negative n plus 2 mg equals m, and in this case it'll be 2m times v squared over r. So this is where keeping track of m and 2m can be useful. The normal force goes to 0, and my 2m, as long as I had it on both sides, will cancel out. And I can see that I get this really typical result for vertical circles, which is that the maximum speed they can have on that hill without losing contact is going to be the square root of g, and I'm going to change that to a capital R because I remembered that's what was given in the problem. So this now, I'm going to mark this as a key result for 1. This is going to be the speed at the top of the second hill. So now let's go ahead and do the second step, which is going to be coming from the top of the hill down to right after the collision. So I just have a change in height, and the height of that hill is r. So in this case, and again, it doesn't matter what's on the initial and final. I'm going to put the top of the hill. So the energy at the top of the hill equals the energy at the bottom. I'm going to add those all up. At the top of the hill, I have mg, and again, this is mass is 2m. The blocks are stuck together. So 2 mg times the height, so 2 mgr, this is my gravitational potential energy, plus 1/2 2m v max squared. where Vmax is the square root of GR. So this then will work out to being G times R times 1/2 times 2m. So that's just mgr. Good. And so then I'm going to set that equal to the sum of the energies at the bottom. The bottom, I don't have any gravitational potential anymore. It's just the speed. So it's 1/2 m v bottom squared. And that m, again, will be 2m. You can see how easy it is to leave it out. So just remembering that that's the total mass stuck together is important. Okay, so at this case, then, I want to solve for this speed, which is the speed of both right after the collision. So if I go ahead and I do that, I can multiply things through and kind of simplify. So I have 2 mgr here. You can see that an m will cancel each place. So 2gr plus gr. So I would have 3gr is going to be equal on this side to v bottom squared. So that gives me v bottom is the square root of 3gr. And I'm going to mark this and label it because I know in my head right now what it is, but by the time I do a couple more steps, I might have forgotten. So I'm going to put in here that this is the speed of both blocks right after the collision. So now I know the speed of both blocks right after the collision. And so I need to then translate that into the speed of just one block. So one comes in, hits, and they move together. So I need to translate that into the speed of just that one block before the collision. So that brings me to my other step, my third step of conservation of linear momentum for the collision. So I have a single mass, m, comes in, and it's going to be hitting my other stationary mass. So that's my before picture. And then after, that turns into both of these moving with what I have called speed v bottom. So being very clear on what speed you're talking about. This is where subscripts are your best friends in terms of labeling things well. So my initial momentum of my system, so I'm going to have just one dimensions here, right? So I just have, let's call this x, p final x. So initially, I'm going to just have m times the speed we're trying to find. You know, again, I don't care what you call it. I'm going to just call this mv before the collision, right? Why not? And then plus this other mass, which was at rest, so its initial speed was 0. I could have had a problem where it was headed towards the other one and then they collided, but that didn't happen. And then that's going to equal the sum of my total final momentum, which is that they stuck together, so my total mass is 2m, and then they had that speed v bottom. So now I just want to solve for v before is going to be equal to 2 twice v bottom. So 2 times the square root of 3gr. So I can then box that. Again, still not my result, but it's also going to be very useful for, my computer's freezing a little bit, so I'm going to give that a second to catch up and see if that helps. Yes, it does. Okay. So v before 2 times the square root of 3gr, and then this is the speed immediately of just m immediately before the collision. Awesome. So last step. We now have used Newton's second law, gotten the speed at the top, translated that with conservation of energy to a speed right after the collision, conservation of linear momentum. Now we know the speed right before the collision. Now we have one last energy step, a change in height, to get our final result. So let's go ahead and do that. So step 4 will be conservation of energy. And so I'm going to say the sum of all the energy at the bottom before the collision is equal to the sum of all energy at the top of the first hill. I can't do energy from the top of the first hill to the top of the second hill because I have a collision in the way. Every time I have a collision, what that does is it basically takes what would have been a nice one-step conservation of energy problem and it turns it into 3 steps. Energy, momentum, energy. There's no way around it because mechanical energy is not conserved in that collision and we do not know how much energy was lost until we do our momentum step. Okay, so right before, this is now to remind us of the picture, this is going to be the energy from right before the collision to the energy that we had to start with. And that's the height we're trying to find. So energy right before the collision is simply going to be 1/2 mv before quantity squared. No potential energy or anything like that. And then I start at rest at the top of the hill. So this is just going to be equal to m. And again, it's just a single mass now, g times h max. So I can go ahead and plug in for my v before. So I end up here with my m's canceling. And I'm going to again end up with 4, because I'm going to square it, times then 3gr all over 2g. And so you can see that this then, if I'm solving for h max, is going to be equal to 6 times r. And that, finally, is my result for the maximum height of the first hill so that it does not lose contact with the second hill. All right, let me know if you have any questions.